And we're going to start with some iClicker questions. And they're actually going to be leading you up to another deluxe practice assignment that I haven't created yet. It's going to be assignment 7.2. And it's going to be more tables and stuff, but it's going to be even more complex than 7.1. So you have your clickers ready. We're going to talk about center of mass and inertia. And really the best way of doing that is to show you some demonstrations on YouTube. And hopefully next Tuesday I'll get some equipment in here. And what you see on YouTube today, hopefully we'll be able to get the equipment and do it in person on Tuesday next week. We'll have some homework, but before we do that, let me just point something out. I've updated this page in Webcourses. It's called Rough Schedule of Topics and Readings. Not sure if you've noticed it or noticed the update, but it is linked to the homepage. Here's the link to it in case you haven't noticed it. Down here, item 6 in our homepage. And here's the folks. It just says Rough Schedule of Topics and Readings. And I normally do not do this. Publish the, fellas. Okay. I normally don't publish the teaching schedule ahead of time because I don't know it. But I've been trying to keep to it, and I have kept to it. And so this is when you click through, it looks something like this. And down here is where we are. So we're on lecture 12 today, angular momentum and angular velocity. And I made this up a little bit before Tuesday lecture, so the descriptions are pretty approximate. But the reading over there, chapter 5, yeah. And if you follow along and you observe the lecture, there's all kinds of cues in the lecture itself. Also, when Darian and Caroline are tweeting on the Twitter feed, you'll see reading cues as well, like page 74, something like that. All right, so for those of you that like to be organized with your study, make sure you look at that, and hopefully, it'll be helpful to you. I was looking through some of my old Keynote files, and I found this one from a few semesters ago. It's a stamp, Deutsche Bundespost. That's the German post office in Germany. And it's in honor of Sir Isaac Newton. Notice the equation up here, delta mv in parentheses equals F delta T. Yeah. That's the impulse equation. And we were talking about that in office hours yesterday. Some of the guys and some of the gals were there. And we talked about all kinds of things. So remember, the office hours are really good to study if you can make them. It's definitely, and there's plenty of space. Well, there's not space for everybody in here, but yesterday there was plenty of extra seats and stuff. We use a little solarium right next to my main office, and it works out good. From 11 a.m. to 1 p.m. on Wednesdays. All right, a few clicker questions. And what I want you to do with these clicker questions, jot them down, and we're going to talk about them. And I want you to not just jot down the questions, but jot down notes about the discussion that follow each question, because these questions that we're about to do are kind of brain burners. They're multiple choice, but we're going to talk about the different options. So here we go. Go ahead and start your clickers. Hopefully you've got, Anybody get Go Nitro? Raise your hand if you got Go Nitro. Okay, good. That means we're good. Don't do anything. All right. Just keep it there until you stop. Darian is up here operating the clicker device this morning. Hopefully this will all work out nicely. How do you know that this is a pop-up? Straight up and straight down. So go ahead and vote. And we're going to talk about each of these options. You know what the thing is? We can't really show the students which option they voted for. Okay, we're going to have to refine this. Maybe I can just do my entire. I hate using a Windows computer though. Whoa.
You could just tell them.
What?
You could just tell them when you pull it up.
What do you mean, verbally?
Yeah.
Students, but that would require students to listen.
I know.
It's like it's almost as bad as asking them to look at the syllabus or that other four-letter word, S-T-U-D-Y. Wait a minute.
Yeah.
It's a five-letter word. Gosh, I typed that in. I was giving somebody the business in discussions. And I said study is a four-letter word. All right, 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, pop the little histogram. All right, now, whoa, a lot of you voted for C. Some of you voted for A. 4% of you voted for B. 15% of you voted for D. And 10% of you voted for E. All right, now the correct answer, keep that up, don't do anything, is C. Make a note of that, and I want to talk about these different options. First of all, option A, a bunch of you did vote for that, 17%. Option A is not sufficient. Option A could be true, and it might still not be a pop-up. Now, what could you have for the initial y component of the velocity and still not have a pop-up? What values of VIY? 0 or negative, yeah. If you had double zeros, that means it's at rest. Okay, so it's not going anywhere. You could have 0 and a negative, so VIY might be negative 5 meters per second or something like that. And so just A by here's your wisdom, statement of wisdom. Just A by itself is not sufficient. It's necessary, but it's not sufficient. Same thing with B. B is not sufficient. Yeah, it's going upward, but you don't know if it's also got any VIX. So make a note for option B. It's necessary to have a positive number for VIY, but if you also have a positive or a negative number, a leftward going, like a foul ball, those will cut behind the batter instead of going out to the outfield. If you've got a little bit of VIX, either positive or negative, you don't have a pop-up. And so just VIY being a positive 20 or a positive 6 or anything like that is not sufficient. So make a note, necessary but not sufficient. All right, now both of them are necessary, and therefore option C is correct. But now let's look at option D. VI is not negative. Okay, so that means VIY could be either 0, in which case you aren't going anywhere, upwards anyways, or it could be negative. You're trying to, a VIY that's negative, a lot of times you see a baseball batter, they'll hit it, and then it'll go straight, they hit it at just the right angle, and it'll go straight down, and it might hit their foot, So, or it might just bounce off home plate. And then they got to run because that's good. Any baseball players in here? Okay, if the ball hits home plate, is that considered in the field of play? Okay, so hitting home plate is a foul ball. But that doesn't mean if you hit the ball out in front of home plate and it goes straight out, then the umpire is going to say, that you better run to first base if you hit just a little bit in front of that. So, so negative VIY, and then option E, neither VIX nor VIY are negative. Yeah, those ones don't compute for a pop-up for the same reasons. Now, I want you to make a final note, kind of a side note for this question. And that is, we decided this question, or you decided the question, hopefully, by looking at the velocity components, both of them, VIX and VIY. The initial X component of the velocity and the initial Y component of the velocity. To determine a pop-up, you've got to know. To determine if it's heading for the outfield, you've got to know both. To determine if it's being fouled back into the screen, you got to know both. To determine if it's going to bounce off home plate straight down, you got to know both. All right? And so it's important to figure out the future state. You at least have to know the initial conditions, VIX and VIY. All right, questions? Not yet. Questions about this before we continue? All right, let's keep going. Next question. If the initial velocity has a vertical component, all right, go ahead. How long will it remain in the air? In other words, what's the hang time? In the NFL, they'd say, well, what's your hang time? For the punter. A punter with a good hang time means all the other guys can run down the field and tackle tackle the guy that's trying to catch the punt. And in my diagram here, I've included, go ahead and write down a picture of a baseball or something with an upward arrow. Doesn't have to be any specific length because we're not really looking at a sequence, but it does have to be straight upward. Okay, this is the pop-up. And we're not looking at a sequence of velocities. Well, we're not drawing in the diagrams for it. So just draw an arrow. And then this is actually another way to write down the vector v subscript I. A stack of 3 numbers, each of them a number of meters per second. And for a pop-up, the X and the Z are both zeros. And the Y is positive. All right, 15 seconds. Now we're going to go over the exact way to solve this in just a second. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. You know, Darian is a lot meaner than me. As soon as I say 0, she clicks it. And when I say 0 in class, usually I give you guys another couple seconds. But not Darian, boy, I tell you what. All right. How many, let me see what the histogram is here. Ooh, 42% of you voted for A, 42% of you voted for B, and then a sprinkling of C and D. Correct answer, B. Now, let me show you how it works. We're going to work it out on several different levels. First of all, on the way up, it loses all of its upward speed. And it loses 9.8 meters per second of upward speed for every second that it's on the way up. All right? So in the first second, it's down to 10.2. By the end of the second of motion, it's down to 0.4. So it needs just a little bit more than 2 seconds to get all the way to the top, to apogee. So you could say the rise time is about 2 seconds. All right? Now, you may have been thinking about that if you answered option A. Right? So if you answered option A, make sure you distinguish between the rise time and the hang time. Now, this is a case we're neglecting air resistance. So it's one of those areas where the Lord giveth and the Lord taketh away. All right, so you take a thing away on the way up and give the thing back at the same rate on the way back down. So whatever the rise time is, in this case about 2 seconds, the hang time, the total time in the air, is double that. All right, so make a note of that. All right. I'm just watching a student over here explain it to his next door neighbor. Excellent. I love it. Thank you for doing that. Good. When you guys are working on these and stuff, I definitely encourage you to interact with your neighbor. If your neighbor's awake, give them, or if they're not, just kind of give them a nudge with your elbow. Not too hard, just a friendly nudge. Now, let's look at the equations. I know you guys are always, worried up about equations and stuff. So let's look at the equations. The one that you need to use is this one. And this is all tricked out all the way. Delta Vy equals G delta T. Okay? That's the amount of change in the y component of the velocity because of the acceleration in the y direction, g. All right, so that's the equation that you're going to use. How come we don't have to do anything with delta v subscript x? Why don't we do anything with the x component of the velocity? Why is that? No, I want to know an answer. Here in the third row, yeah. No, you. There's no horizontal velocity? No, it's not that there's no horizontal velocity. We know that. It is a pop-up. How would you say it? Right, there's no horizontal gravity. Okay, is that what you were fishing for? Yeah, okay. Now, someone had a question in the back. Brooke!
Yes. Is that equation for
The reason I know Brooke's name is because she came to office hours yesterday. So now she's embarrassed completely. That's all right. Go ahead.
Is that equation for rise time?
Yeah, that's the way that I'm going to do it. But you could actually, it depends on what you put in for delta Vy. All right? Now, I'm going to do it for rise time. All right? So now, first I'm going to do is get g to the other side of the equation and get delta t by itself. But Brooke, yeah, you could use this for hang time if you want, and I'll show you how to modify it. Now for rise time, you're going from positive 20 to 0. Okay, that's the rise. And then after that is the fall. Right? So from positive 20, that's V1, and 0 is V2. So delta V subscript Y is 0 minus 20 meters per second. All right, so now, Brooke, if you were going to do the entire hang time, all you have to do is put a 20 in here. Or, excuse me, a minus 20. Because when it returns to Earth, Brooke, you're going the same speed downward as you started upward. So you'd have a minus 20 instead of the 0. Right? Minus 20, subtract 20 from that, that's negative 40. Divide that by negative 9.8, and you'd have the total hang time. But for the rise time, it's this, 2.04 seconds. So your basic answer is 4.08. Now, the little rounded rectangle on the left, in the lower left corner, where it says the rise time is about 2 seconds, that's a sentence, that's an English sentence that expresses the fact that you can kind of mentally estimate. And how do I explain that? Well, gravity takes away 9.8 meters per second of upward speed for every second that you're on the way up. Okay? So the one way you could think about it is, for every 10 meters per second of upward speed, you need a second to lose all of it. So if you have 30 meters per second of upward speed to start, you're going to need about 3 seconds. 400 meters per second, that's really going, of upward speed, you're going to need about 40 seconds to lose all of it. That'd be pretty good. 40 seconds going straight up. Man. All right, so that's how you would work that out. 400 meters per second, that'd be about 800 and something miles an hour. That's a pretty good, and then it'd be going up for 40 seconds. But anyway, so for rise time, if you have 15 meters per second of upward speed, your rise time is going to be about 1.5 seconds, right in there. 15 divided by 10, and that gives you. And just make a note to yourself. That's an estimate. This set of equations tells you how to get the exact number, to however many digits you want. Question.
It's 4 because it rises to 4.
Yeah, it's 4 because this is the rise time calculation. And so do the rise time calculation this way. Either do it mentally, like I did in the rectangles on the left, or do it this way and get a good solid 2.04 and then double it. Or as Brooke was saying, can you do the entire thing in one calculation? The answer is yes. If you put negative 20 here instead of 0 meters per second, because that's your final speed. All right. So the final speed, when you're all the way through the motion, is negative 20. Mm-hmm. But your final speed, if you're just thinking in terms of half of the motion, the final speed is 0. So that's how I do it. But you can use Brooke's method if you want. Another question. Okay, let's keep going. You can close that.
My clicker in general.
Mm-hmm. And you can select the other thing that we're going to do.
Oh, okay.
don't minimize it. You can, definitely, yeah, you're going to have to keep it good for next class. Okay, let's get back to talking about angular momentum. This is a diagram here from page 74 that we're going to talk about in a few minutes. But before we do that, I want to take a look at some angular momentum videos in YouTube. And go to the PSC 1121 YouTube area. Same place as you have the lectures. And one of the other playlists is angular momentum. And we're going to look at some of those right now. So let me pause the podcast and we'll go to the videotape. Yeah. Bring it back to the, okay, that's it, the right one. All right. Okay, so you can look at that in Webcourses. Now let's get some notes, some more notes. And I actually want to talk about this diagram in the textbook at length. This is from page 74, as I mentioned. And it is a diagram about a board floating in a pool of water. So it's supported by the buoyancy force of the water and a little bit of rigidity force of the water against gravity, but horizontally it's free to spin or to move in any direction. One of the things that we've kind of made an assumption about is that everything moves as if it's a point object. So, for instance, baseballs and cannonballs and stuff. And that's just because they're rigid and they're spherical. So when you apply the force, any kind of a force to a baseball or a billiard ball or something like that, you're really applying a force like F1 through the center of mass of the billiard ball. There's a little bit of friction on a billiard ball. There's a little bit of friction on a baseball, so you can get a spin on it. But basically, that's the case. Now, if you have a real object, the trajectory can be quite a bit different. And of course, it depends. The motion of the object depends on F equals ma, but it also depends on torque effects. So if you were to take this board at point C and heave it through the air, it wouldn't spin. But if you took this board at point A and hove it through the air, and that's what you do. What kind of a thing? Oh, okay. If you ever watch on like ESPN, they have these. Do they? I don't have ESPN, but sometimes you see these lumberjack contests. Do they have those on ESPN? Well, they have Strongest Man, I know, but they have lumberjack. And one of the things in the lumberjack is they throw an axe. So if they try to get it into a tree or something like that. Okay, that's the lumberjack contest. So if you're a lumberjack, you can throw, the center of mass is going to be up around the axe head because most of the mass, it's really heavy. But if you throw it by the handle, it's going to fly through the air and hopefully it'll stick in the tree. Now, this is what happens. Go ahead and take a look at this. And I don't know, God bless you, I don't think you can make a diagram of this for your notes. But go ahead and make a note. It's a strobe photo of a crescent wrench. This is an overhead view of it. And it's not a perfect, but what I want you to do is look at this carefully. And I'm going to move my cursor over to this far left image, okay? The far left image of the wrench tilted to the left about 20 degrees. Now, do you see that where my cursor is there? Do you see that little kind of black diamond painted onto right below the twisty part of the wrench? You see that? Right about here? That's the center of mass. It's not in the exact center of the wrench because there's a lot. It's over close to the head of the wrench because there's a lot more metal over there, right? So the center of mass is over there, and I put a set of dots. You can see in this strobe photo that that diamond moves. It's been, somewhere off here to the left, outside the picture. It was thrown through a point, or a force was applied to it through a point, not at the center of mass. But the center of mass moves at a regular speed. And I made a set of diamonds. Hopefully you can see these a little bit better. Look at how regularly spaced they are. All right, there they are. That's the center of mass of that wrench. Now, this is what I call a complex motion. There's a lot of 1/2 mv squared. There's a lot of delta P going on here. There's a centripetal accelerations going on, the rigidity of this wrench. But the center of mass is just kind of moseying along. Look at that. Those diamonds, those kind of bluish diamonds with the white outline, they're regularly spaced. This is a strobe photo. It's an overhead view. So this represents a horizontal motion. There's no acceleration, and those dots are evenly spaced. Right? So make a note of that. Overhead view, the motion is horizontal. The center of mass, delta x equals v delta t. Nice and easy, nice and smooth. But the rest of the, as Paul Harvey used to say, the rest of the story, the rest of this wrench is in complex motion. It spins about the center of mass as it goes, and you can see that. It starts over here, the leftmost image. The wrench is tilted a little bit to the left, about 20 degrees, but over here, let's see, 2, 3, 4, 5, 6, 7th image, it's almost 180 degrees away from, and the 8th image, it is 180 degrees different, right? So in 1, 2, 3, 4, 5, 6, 7 flashes of the strobe, this thing has spun 180 degrees, and it just keeps spinning. All right? Yeah, here's a cool photo. Well, before I show you this photo, let me ask you a question. Raise your hand if you have a motorcycle. You ride it. There's nobody in here that rides a motorcycle? Raise your hand if you've ever ridden a motorcycle. Okay, so that's better. All right. Have you ever done this? Like this guy? Whoa. Woo! Man, look at that guy. But if you think about it, this is a complex motion. Here's another picture. I think it's a different guy, but it's the same kind of a stunt. And the center of mass of the man motorcycle system, go ahead and make a note of it. Okay, this is a complex motion. The center of mass is a simple parabolic arc, just like a baseball or a cannonball. So make a note of that. Center of mass, a walk in the park, just a regular parabola, just like a baseball. But the rest of the story, the rest of the motorcycle and this guy who, oh man, and see, look, he over here on the left, there he is landing. He survived that. He did it just right. Can you imagine what would happen if your spin rate was not right? Gosh, you could come down on your head. And that's it. I mean, you come down here, you do this, and see, because look, right about here, now here's his head on top. Gosh, can you imagine what that's like? I wonder if he closed his eyes when he did that. Can you imagine what that's like up here? The view at that instant? But here he is. Let's see, right about here, his head is downward. And I don't know, it's kind of hard to tell. Anyways, he lands just right over here. Gosh. Oh, he's doing it back? Ooh! I don't even want to think about, I don't even like looking at this picture. I'm not looking at it anymore. It's going to make me. All right, so this is another thing that there's actually something mysterious about this. And that is the F equals ma forces and the tau equals I alpha torques, they act independently. It's almost like, it is like there's another way to change the dynamical state of an object. So this thing, very simple force, very simple net force, basically it's just gravity downward, mg, and that gives him the parabolic arc. But boy, the torques and stuff, and his angular momentum state all through the torque, the fact that he's spinning independent. You know, he could do this thing without spinning. I mean, you sometimes see photos of guys doing, you know, like actually the homework image. That was a photo of Evel Knievel from like 40 years ago, jumping over a bunch of, I don't know what it was, buses or something like that. And he did that so that he didn't spin. This guy's doing a backflip. So you can do it without a backflip or you can do it with a backflip. They're independent. So make a note of that. Spin state, angular momentum state, independent of linear momentum state. And it's kind of a cool thing to think about. Now, let's talk about the specs on the moment of inertia. The moment of inertia is basically this. As I've mentioned before, it's the sum of mr squared for each pixel of matter. So if you think about these dumbbells down here as being pixelated, right? And you break it down. So in other words, gram by gram. You know, every half of a cubic centimeter or so is going to be a gram of steel for these two dumbbells. Okay, and each gram of steel has an R value from this spin axis, the dotted line. Now these two dumbbells, and this is a diagram from your textbook too. I can't remember exactly which page, but this first dumbbell on the left, all right, the same size weights, so the same number of grams, but they're only 22.5 centimeters from the spin axis. Now this other one down here on the bottom right, it's a little bit bigger, 60 centimeters across. And so most of the pixels of mass, most of those single grams of mass are either 30 centimeters to the left or 30 centimeters to the right. Okay, so this one on the right has a bigger moment of inertia because r squared is bigger. All right. And what I'm going to do for your homework over the weekend is give you some moment of inertia problems. And I'm going to kind of guide you through a set of steps so you can make some decisions about moment of inertia. And then from that, you're going to make decisions about L equals I omega. And make a note of it. This formula for angular momentum, this is the formula that helps you understand all of those YouTube videos that we looked at. All of them. Right? Any questions about these formulas before we continue onwards? We've got a few more things to talk about. Here's a picture of an SSG group, special study group. Remember, exam 2 is coming up on the 13th. If you do really well, if your 2 exam totals add up to 90 between exam 1 and exam 2, then I'll probably invite you to be a leader of an SSG. And there they are, the 7 smiling faces. Okay, let's dismiss homework 8. I'll activate it tonight. We'll see you on Tuesday. You're dismissed. A few minutes early today.